Hi guys, this is Kinetics 106, and the topic is applications and examples with integrated rate laws. Your homework is still the chapter 14 PS 3 and 4, and I just wanted to do a really quick review before I get started with the examples, and that review contains the following points. The first is that integrated rate laws show concentration of A at time t as a function of time. So we would say A sub t equals f of t. There are three forms of integrated rate laws depending on the order. If it's zero order, the rate law looks like this. A sub t equals negative kt plus a naught. If it's first order, we have a natural log component there. And if it's second order, then it's an inverse component. To determine the order, just plot the three relationships, linear regression, both of them. The one with the r squared value that's closest to 1.0 tells you which order it is. So if A sub t concentration versus time is most linear, then it's zero order. If it's natural log of concentration versus time is most linear, then it's first order. And if it's 1 over concentration of A sub t versus time is most linear, then it's second order. Okay, so that's kind of a little review for you. And I'm just going to hop into an example of using these rate laws. Okay, so this is part one. This is examples 1 and 2. And here is example number 1. We're going to say a reaction is known to be first order in A and have a rate constant of 0.0568. If the original concentration of A, so A sub naught, is equal to 0.750 molar, how many seconds will it take to reach 0.457 molar? Okay, so we have an initial concentration, we have a rate constant, 0.0568, and that's going to be given to us in 1 over seconds, right? And we want to know if the original concentration is 0.750, how many seconds will it take to reach 0.457? Okay, so they've done kind of the hard work for us here. They've already diagnosed what order it is. We know it's first order, so we know we're going to use natural log of A at time t is equal to negative kt plus natural log A naught. So we're just going to substitute and solve for our unknown. And our unknown in this case is time, right? So we're going to go natural log of A at time t, and that's going to be the 0.457. Make those rounded. And it's equal to negative k, which is 0.0568. And then t is our unknown, plus natural log of our original concentration, which is 0.750. So we have this expression in which we've got natural logs and time. I gotta grab my calculator. So we're gonna go ahead and just evaluate that. So you do natural log of 0.457, and here we get negative 0.7831 is equal to negative 0.0568 t plus natural log of 0.750, and that's negative 0.2877. Okay, and so I'm going to do a little bit of baby algebra here. 0.2877 plus 0.2877, that goes away. And we have negative 0.7831 plus 0.2877 equals, and we get negative 0.4954 equals negative 0.0568 times time. So again, a little bit more baby algebra. Divide by negative 0.0568. Okay, so our time comes out to be 8.72 seconds. Okay, I think you can see that. So that's example 1, and you guys can rewind or pause or wherever you want to do. I'm going to go ahead and go on to example 2. I'm going to lift this up, sorry about that. Okay, and so our example 2, technical difficulties with my pens here. Example number 2, we are going to have another first order reaction. So we have a reaction is first order in A, and we know the rate constant is equal to 0.875, and we know if A naught is equal to 1.5 molar, what is A sub T after 2 seconds? Okay, so we know again it's first order, so we know we're going to use our natural log capabilities here. We know that natural log of A at time t is equal to opposite k, t plus natural log of A naught. So this is our unknown, right? Well, A sub t is our unknown. We're trying to find that. So we're going to have to do a little bit of natural log undoing. So let's substitute our k here, 0.875 times the time, which is going to be 2 seconds, plus natural log of A naught, which is 1.5 molar. Okay, so over here is our unknown. We're just going to evaluate this. So natural log of 1.5, and I'm just going to bring this down. Natural log of 1.5 is 0.405, and 0.875 times 2, and this gives me 1.75, and that's our natural log A sub t. Okay, and this is opposite, of course. So we're going to have negative 1.75 plus 0.405. And we get natural log of A sub t is equal to negative 1.345. Okay? And then if I want to solve for A sub t, which is what I want to do, I'm going to have to undo this natural log. And in order to do that, we're going to raise e to both sides. So e to both sides undoes the natural log there, and we end up with A sub t. So on your calculator, you're going to use this function right here, that function right there, which is the opposite of the natural log. So you'd go second function e, and that opens the window for you to see e to the, and then put in your value, negative 1.345, close brackets, enter. And your A sub t comes out to be 2.61, and that's going to be in molarities. Okay, so that's another example where you're solving, instead of solving for time or something else, here you solve for A sub t. And that's it for part 1. Thank you.